o'clock, so let me hand over to the chair, Florian Bernlachner.
Thank you very much. Yeah, welcome to the plenary session this morning. We'll have 3 talks scheduled, and the first talk is from Umberto Tamponi that will give us an experimental review on spectroscopy. Umberto is from Torino, and with that I'll hand over to him, and we're looking forward to your talk.
Okay, thank you very much. I hope you see everything properly.
Yes, we do. Please.
Okay, excellent. So I have, well, it's a pleasure to be here, but I have a quite challenging talk to give, honestly. So in principle, I should give you a complete overview of the experimental status on Hadron spectroscopy, which I also think it's not really the core business of this conference. So I will start with a more general introduction about the status of hadronic physics in general. Then I will give you some news about especially heavy hadron spectroscopy, and then I will move on to prospects for the future. And the next talk will be about the theoretical aspects of this kind of physics. However, since I'm the first one to talk, I thought it was a nice idea to start with a brief introduction about how we what's the general interplay between experiment and theory in this field, because it's slightly different from what you are used to in Higgs physics, for example. So our problem is that we are intimately dealing with the non-perturbative aspects of QCD, which is a theory we have, but we cannot solve, at least not directly. So instead of having direct prediction from the standard model Lagrangian, what we have is are predictions from a quite large number of models which are approximating in a more rough or more refined way the behavior of the non-perturbative QCD. The ultimate goal of spectroscopy in, I don't know how many hundreds of years from now, of course, is to corner which approach is the correct one, and in this way try to crack the solution of non-perturbative QCD. One of the aspects of the drawbacks of this situation is that we have an incredibly large amount of theoretical predictions. Basically, for each state, you have several authors, and then you have to multiply by the number of models that you have. So you end up with a probably 1-to-10 ratio between experimental paper and theory papers. The other aspect is that since these are effective theories, we have a close feedback loop between theory and experiment. Sometimes we discover things which were predicted since the dawn of time, basically, like the pentaquarks as a concept. And some other times we discover stuff which was completely unpredicted so far, like the X3872. And we feed back this information to the theory models that will adapt somehow and will produce new predictions. It's a quite exciting place to be, actually, because discovering things that you don't expect is always nice. Okay, these are concepts that apply all over the spectrum of hadrons. However, since you're ranging from the pion mass to the Upsilon 6s mass and maybe even beyond, you are probing completely different energy scales, and this gives you quite different behaviors and quite different tools for interpreting the results that you have. In general, what we divide is the light hadron sector from the heavy hadron sector. So light hadrons are the SU3 flavor ones, UDS, mesons, baryons, and whatever you want. Since SU3 of flavor is basically fine as soon as you are limited to light quarks, what dominates your interpretation of these states is the arrangement of multiplets, of flavor multiplets, rather than energy spectra, for example. You have an system which is intrinsically relativistic, because if you think about the quarks, the binding energy of the quarks is of the same scale or even much higher scale than the mass of the quarks themselves, meaning that you have to deal with relativity, and L by itself is not a good quantum number as a consequence. If you move to the heavy hadron sector, suddenly things are, in a way, much simpler. First of all, the flavor symmetry is completely broken. So you can disentangle the quark content by looking at the decay products, and if you have a C or a B meson, they won't mix with each other. the energy, the binding energy is much smaller than the constituent quark mass, meaning that the system is not relativistic. That gives you more selection rules, like the heavy quark spin symmetry, and a way to arrange state which is more clear, because L is a good quantum number. You have a nice spectra like you have in the hydrogen molecule, for example, hydrogen atom, for example. From the point of view of the experiment, also the tools that you use for probing different energy scales are different. These are more or less all the tools that we have in our toolbox, from photo production to E plus E minus scans, quarkonium decay, etc. And each of them applies to different regions. So for the reasons I mentioned before, and for my personal background, honestly, in this talk, I will not talk about the light sector. I will also exclude the charm meson and charm baryons by itself. I will focus more on the heavy quark mesons and what we learn from them. Apart from personal biases, one of the reasons why I want to focus on this is that in the past 10 years, let's say, we discovered something like 5 new states every year on a pretty regular basis. This plot comes from LHCb only. You should add also Babar and Bell to this, and Best 3 to this game. And the reason why we discovered so many states is that we are basically probing something beyond the good old meson-baryon distinctions, and we're seeing states which are definitely made of more than 3 quarks. So we have pentaquarks, tetraquarks, possibly molecules, if you want to go into the details of the single models. And the reason why we are discovering them now instead of 20 years ago is partially due to what I was telling you before. The heavy hadrons are easier than the light hadrons in some sense. Of course, this goes back to this idea. The tools that we have for heavy hadron, the theoretical tools, are not usually developed, were not developed at the beginning for heavy hadrons. They were developed for light hadrons. I'm pretty fond of this diquark anti-diquark model, the so-called compact tetraquark model. It's a very personal preference, and I don't want to bias too much my talk. However, this was developed for the light meson spectrum. It should explain why you have a flipped mass hierarchy in the scalar mesons. The point is that after years and years of investigation, you don't have a smoking gun in the light sector to distinguish between 2 quarks and 4 quark states. On the other hand, when you go to heavy hadrons, you have these smoking guns. And the reason is pretty intuitive at the end. So imagine you have something, a state, which has these 3 qualities: large mass, narrow width, and decays into a CC bar pair plus whatever you want. Since this guy is decaying strongly, you must have the CC bar pair also inside the original particle, okay? So that's a starting point. At this point, you just look at what you have produced together with the CC bar pair. If you have produced a strange meson or a charged pion, then you must have 4 quarks in the initial state, arranged in the way that you prefer. They could be 2 diquarks or 2 neutral mesons talking to each other via residual force. That's a different matter. However, you still have 4 quarks at the end. If you're producing together with the CC bar pair something which is neutral from the point of view of everything, then you can either have a tetraquark or a conventional meson, but you can distinguish between these 2 guys because for conventional mesons you have pretty accurate predictions for the mass spectra that you expect. So if you find something that doesn't fit the place that it should fit in the spectrum, you have an exotic. And the same thing goes for pentaquarks, in which you have a baryon, so this guy must be a baryon plus a CC bar pair. Pretty easy, pretty intuitive, at least in my opinion. So this is the overall status. This is why I like heavy hadron spectroscopy. And let's go to the news in the sector. I have to apologize. I will dump a number of weird names because we follow this annoying convention to call the states with a letter, something about the quark content, and then the mass. And the mass down to the MEV level, okay? So getting confused is pretty common, let's say. However, In the past couple of years, we had three very important discoveries. The first one is the one of the discovery of strange charmed tetraquarks. This was done first by BESS3, that saw something decaying into this star, this abyss. So this guy, following the previous rules, must contain the CC bar pair and a strange quark. And then you need, of course, another anti-quark. So this must be a tetraquark because you have the strangeness instead of having the charge and so on and so forth. I think immediately after, probably basically at the same time, also LHCb discovered two different states which also have strangeness. In this case, they decay in K J psi, while the first one decays into the star this abyss. The reason why we are so excited about finding these states, which just pile up with the other dozens of states we have, is that there is a specific model, which is the compact tetraquark model I was talking about, that predicts flavor multiplets for the tetraquarks. Okay, the concept is the same that you have with quarks, just with diquarks, so you have more stuff. And what you have as a baseline for the charmed tetraquarks are three nonets with different quantum numbers. So far, in orange here, you have the states that we discovered, and the new guys are sitting here at the corners of these hexagons. So discovering them with roughly the masses that you would expect from the mass formulas for diquarks are basically telling you that maybe these multiplets are something that is telling you that maybe the tetraquark model is something that really reflects reality. It's not done yet. There are many problems with the tetraquark model. However, it's the first very interesting hint in this direction. I'll have more to talk about that later in the last part of this talk. The second news is that, again, we have strangeness, but this time in pentaquarks. So, as I told you, pentaquarks were discovered in J psi plus a proton. And then we have now a new J psi proton pentaquark, this PC number down here, discovered in B-sub-S decays. And we have possibly a pentaquark in J psi lambda. So again, if you think about diquarks and if you think about flavor multiplets, this guy would fill up different spots in your nicely arranged multiplets. However, we only have 5 pentaquarks so far, so it's definitely too early to start talking about filling them up. Then, a very interesting thing, at least to me, I was very jealous of LHCb for finding this, is the resonance in, oh, sorry, this is 6,900, is a resonance in J psi, J psi. So this is a state, narrow state, that decays into a couple of charmonium, meaning this is the so-called fully heavy state. This is C bar guy. There is one narrow here. Possibly there is also something, I mean, not possibly, definitely there is something else going on at the threshold. Here you have different models that LHCb used to fit the threshold. We don't know exactly what it is. Can be fit down from other states, can be a broader state, just right there. Just to tell you, in little more than 1 year, we have order of 100 theoretical interpretations for this guy, covering all the possible models, of course. But this is the beginning of a whole new sector of spectroscopy, because if this guy exists, then there must be radial excitation, P-wave states, and so on and so forth, that we should explore by looking at J psi, pi pi, and so on and so forth. And finally, I'm approaching the biggest news of the year. We are exploring the double charmed sector. So far, all I told you was about states which have hidden flavor. So they are CC bar or BP bar. However, you don't see the charm, you don't see the beauty exposed. In 2017, LHCb discovered a state which was predicted since I don't know how many decades, which is the cascade CC++. This is a baryon made of 2 charm quark. Okay, it's the first charmed, doubly charmed object discovered, and so immediately the hunt for the other guys, the Cascade Plus and the Omega Plus, started. And this year, actually, this conference, it was also presented, I think on Monday, we have hints, not evidences, but hints for these two guys showing up. These are fully conventional states. They're not exotic, however, they have a lot to do with the exotics. And again, put a pin in this because we will talk about that later on. And finally, the last, the most important news of the year is the discovery of the TCC. So the TCC is a doubly charmed tetraquark. It decays into DD star, and I didn't forget a bar here. These are same flavor D mesons. Okay, so this guy is something like CC and then light quarks. It's narrow. It stays down here at the threshold, basically for the DD star production. It should be 1+ if you assume that decay happens in S wave, but determining the quantum numbers is actually a problem that we have. And you don't see anything in the isospin partner channel D+, which is something that was predicted by, again, the tetraquark model. So if you ask some theoretician, if you ask Marek Karliner, for example, he will probably tell you that this is the most important thing we discovered in the past years and will change everything, because finally we have evidence for these states that were predicted but not observed so far. And it's a completely new spectroscopy we are starting to probe only now. Okay, I hope I didn't flooded you with too many weird names of new particles. For the next part, probably it will be slightly easy. It's also the last part of my talk, the longest one, and it's about what we are planning to do for the future. So what we should expect from the experiment in this sector. So the things we can do are basically three. It's trivial, but that's it. We can either measure the properties of the states that we know. We can try to replicate the experiments, the results of other experiments. And I think that this is a very crucial part, which is also really overlooked by high energy physics community in general. And then we can try to discover new stuff, which is the most exciting bit. Since discovery is the most exciting bit, I will start from the most boring one, which is try to assess for properties of this state. The first property that you definitely need to measure if you want to understand the spectrum of these guys are the quantum numbers. Okay, and if you look at the PDG, the situation is pretty depressing. Okay, except for bothonium-like, in which we have the quantum numbers for all the states. At least we have them if we assume the quark model assignment for certain states. The direct measurement of the quantum numbers, even in bothonium, are much less than the nominal ones which are reported on the PDG. However, in the other sectors, you see that sometimes we have basically no measurement at all. In other cases, we are around 75 or 50%. Okay, this is an extremely important piece of information, because if you think about these flavor multiplets, you need to know in which multiplet you have to put your state, and so you need to determine JPC. So the task for the next year, in my opinion, is try to do this tricky and possibly boring task all over the place, and measure JPC for all the states that you have measured so far. Now, there is a reason why this situation is not so nice, and it's well explained by the pentaquark case. Okay, so when you do, usually these states appear in Dalitz decays of something else, like the pentaquark appeared in the Dalitz decay of the lambda B. So if you want to determine the quantum numbers of this guy, what you have to do is a full amplitude analysis of these Dalitz, okay? And in 2015, when we thought that only 2 pentaquark states were there, this narrow-ish guy here and then something broad, there was the full amplitude analysis was done immediately in the first paper, and we got a measurement of the quantum numbers of these states. However, this was done under the assumption that the width of these guys is larger than the experimental resolution. Now with more data, LHCb discovered that this peak is actually made up of two different peaks, and this small hint here is not a fluke, it's actually a state. Okay, so from 2 pentaquarks we move to at least 3 pentaquarks, and 3 of them are narrow, and by narrow I mean narrower or as narrow as the experimental resolution, meaning that when you have to do the full amplitude analysis, now you have to model your detector resolution across the whole multidimensional Dalits. And this is conceptually easy, however, it's very challenging from the technical point of view. Basically, the fit takes a long time to converge and a long time to compute, and this is something we also observe in Bell 2 for completely different analysis. And that's the reason why we don't have measurement of the quantum numbers of these guys yet. So I think that we are really approaching a point in which we need shared common tools to do this kind of fit and to do this kind of fit in an efficient way, because doing them is okay, doing them in a reasonable time is extremely hard. So the other thing that we must do in the future is not look for new states, but look for existing states. So if you look at the PDG and if you follow this kind of physics for a long time, you know that we have, okay, thanks Florian, 5 minutes, excellent. You know that we have a lot of states, but if you look at how many of these have been seen in more than one decay mode, more than one production mode, and by more than one experiment, you will end up with, I think, 3 or 4 of them out of 50. Most of these guys have been seen somewhere by someone in a certain production mode. So I think it's extremely important to reinforce our knowledge of these states by looking for what we see, but in different places. There are a number of theoretical ideas. For example, we should look at prompt production of exotica in proton-proton collision, or even at tetraquark produced by basically photon-photon fusion in extremely peripheral heavy ion collisions. Okay, so this is probably not something that will give you a lot of citations because it's a confirmation, a rediscovery. However, it's extremely important from the scientific point of view. And finally, we have to look for new stuff. And what we've done so far, I think it's still working very well. We should just keep looking at bumps in invariant masses of pair of mesons or meson plus dipions. It worked very well so far, so let's keep up with bump hunting everywhere we can. However, with a little bit of guidance from theory. There are a number of things we know we should look for. And one of them, for example, are the other pentaquarks. Again, if you believe in the diquark-diquark model, these pentaquarks will give you at least an octet and a decuplet as a baseline, which are mimicking basically the octet and the decuplet of the baryons. So you should keep looking at resonances in J-psi plus your favorite baryon as a baseline. There are also predictions from molecular models in which you should look for B sub C plus proton or upsilon plus proton. However, this is something that LHC can do, I guess, and all these invariant mass spectra should be immediately explored. Then for the tetraquark case, we have a case for looking for the isospin partner of the X3872, the famous X3872. Basically, the tetraquark model is the only one telling you that this guy is the isospin singlet and has an isospin triplet partner, which I called here ZCs. We looked for them, we didn't find them. However, there are predictions for the production rate of this guy, which are putting them at the limit of our experimental sensitivity at the moment. So I think that the next challenge for the next 5 years of statistics will be really to nail down this case and understand if we have the X3872 isospin triplet partner. And then I told you that we were there was something more about the doubly charmed baryons. And what's more about that is that they basically act as a bridge between conventional and tetraquarks. Because in a doubly charmed baryon, you have a fully conventional state that you understand, but you have the CC diquark, which is the same guy that appears in the TCC, for example. So you can take the information that you have from the spectra of doubly charmed baryon and with some algebra make predictions on the spectra of the doubly charmed tetraquark. This is something that Karliner has done a number of times, and he actually also got correctly the cascade CC++ mass at the first shot. So our experimental task is to complete the spectra of these double charmed baryons and look for more stuff and look for more doubly charmed tetraquark. Now, the very last topic of this talk is about the flavor invariance of QCD, in a sense. So in principle, okay, 1 minute. In principle, every pattern you see with charm should more or less repeat also if you replace the charm quark with the B quark, because QCD is flavor invariant. The advantage is that with B quark, you basically forget about the relativistic corrections, or forget, they are much smaller than in charm, and you have even stronger selection rules. So in principle, you should be much happier from the point of view of understanding your states. From the point of view of experiment, things are much more bleak. At proton-proton collisions, you have a cross-section for B production, which is much, much smaller than the one that you have for charm. So you're limited by statistics. You don't have higher mass mesons, which are decaying into B. So you cannot play the trick of looking at the B to charm decay, because you don't have a meson with top that decays in B. And in the plus and minus collisions, you can scan the bottomonium region, but you are forced to start from an epsilon 1s state. An epsilon ns state. So you are bound by the decay rate of the state that you produce into the exotic. Not to mention that at Bell 2 we are currently limited at 11 GeV, which is basically just a little bit above the threshold for BB production, and at the beginning of the interesting region. So B hadrons are, for these reasons, much, much less known than the charm counterparts. So in the future, I think that LHCb possibly, or LHC in general, in round 3 should look for the TBB, which is a nice guy that might be even stable against electromagnetic and strong interactions. And then, of course, doubly B baryons, dub4B tetraquarks, and so on and so forth. At Bell 2, what we can do is to sit on the highest resonance we can reach and look for radiative or single pion transitions to this number of exotica that were predicted to sit at the different threshold for BB bar meson productions. And this is indeed what we started doing already. We just completed the first non-4S run at Bell 2, where we took data in this region around this bump that was observed by Bell, that could be a conventional state, could be a mix of a D state and a tetraquark. I mean, there is quite some interest about understanding this guy down here. And the results will be probably ready by fall next year. Okay, so these are my conclusions. My main selling points is that it's the fact that we have tetraquark and pentaquark is established experimentally. The point is understanding from the theory point of view what they are. We have 3 experiments which will run for the next decade at least, plus other ones that can provide additional information. And we have a long list of things that we should look for. And yeah, that's it. Thank you very much.
Yeah, thank you very much, Umberto, for the really, really nice overview. I'm sure we have questions. Yeah, Hafiz, please go ahead.
Yeah, my question is that is there anything which challenges the standard model or the quark model?
Depends on what you mean by, so challenging the standard model, as in we discover something which is not embedded into the QCD Lagrangian. I would say no, not in spectroscopy.
Okay.
Unless you start looking at things like fine splitting of states. For example, if you have a light new particle that is located around the hadronic resonance, for example, a light Higgs that sits close to the eta C, for example, then these two guys can mix, and the mixing will shift the eta C and will change the hyperfine splitting that you observe from the theoretical predictions. So you are somehow sensitive to beyond standard model effects, which are shifting around the states that you predict from the quark model. in terms of challenging the quark model, if by quark model you mean the static quark model in which you have baryons and mesons, that has been challenged for good. We have to accept this extension. The real point is now of how far this extension goes. We have 4 quark states, we have 5 quark states, but we have not observed 6 quark states. The dibaryons are sitting there in theory for a very, very long time. And honestly, if we don't observe dibaryons and we still think that dibaryons should exist from the theory point of view, then maybe we have some tension that we should understand.
Okay, fine. Thank you very much.
Okay, I think we have time for one more quick question. John, please.
Could you go into a little bit more detail about how we actually go about measuring the quantum numbers?
Okay, I don't think I have much more than these. So basically what you do is you take the full Dalitz plot of your decay, and if you're lucky, it's it's a 3-body decay usually, and you start putting into it all the possible resonances. For example, in this case, you have a decay which is J-psi proton kaon. Okay, so as a baseline, you have to put inside all the possible lambda excitations which are decaying into proton kaon, and these are I think 20-ish or something like that in the case of the pentaquark. So you have all these amplitudes, you sum them up with the relative phases and so on and so forth. So it's a fit with complex numbers. And you keep adding new resonances until you are satisfied with the result of the fit. In this case, you have to add, for example, these, in the left plot, you have to add these 2 pentaquarks. And it's pretty clear that this is a projection of a multidimensional fit. Because, for example, the narrow pentaquark is very visible as a bump, while the broad pentaquark is basically invisible because this is the bright Wigner shape, but then it's killed by interference with the other resonances that you have. And it gives you this very, very broad distribution. So that's basically how they are done. How technically they're done from the software point of view, honestly, is something I cannot really answer you. I know that people in Bell 2 are still using Fortran-based tools, and I think that LHCb it's more oriented on C++ and RuFit, but I'm not 100% sure about that.
But it's not a partial wave analysis then?
No, as far as I understand, no.
Okay, thank you.
Okay, then let me thank Umberto again. We have to go on though. The next speaker is complementing what we just heard and will give us a Hadron physics theory overview. Sasa Prelovsek from Ljubljana. Please, Sasa, whenever you're ready. In case you're speaking, we cannot hear you. You have to unmute. Yeah, cross-through mic.
Okay, can you hear me now?
Yes, now we can hear you.
Sorry. Okay, well, thanks to Marco and colleagues for great organization, and thanks to Umberto for giving a really nice introduction into this. So, as you've seen in experiments, many interesting states have been discovered, exotic and conventional, and I'll try to convey where theory stands on this. Okay. So today really we know that hadrons with all these minimal quark and gluon contents exist. So of course, as Umberto told you, well, of course there is conventional hadrons. Today we really know that there is also exotic hadrons where there is 10 tetraquarks, pentaquarks, and hybrids, where I just give one example of the discovered state here. Well, they are composed of quarks and gluons, so it should be described by QCD, and the QCD Lagrangians is known. that's not a problem. The problem is that the coupling constant is not small, so one needs a non-perturbative approach. I'll try to focus, where available, on the results from ab initio approaches, which are really based on the QCD Lagrangian, and these are first two. In lattice QCD, what one evaluates is the path integral via numerical path integration, okay, on a finite discretized spacetime. But many of the results that I'll present are still non-precision studies. So the quark masses from the simulations are bigger than in nature. In the second ab initio approach, the Dyson-Schwinger equations are used, where you relate the dressed quark propagators and vertices. And the Bethe-Salpeter equations are used, which relates the scattering matrix and scattering kernels, but there is still some truncations. Honestly speaking, for many of the discovered exotic states, there is no final conclusions yet from these two ab initio approaches, and then I'll talk about the model results. Well, we are composed of protons and neutrons, and well, they constitute more than 99% of the bright side of the universe. And out of this, the Higgs contribution to the valence quark masses is only 10 MeV, so only 1%. In spite of this, lattice studies now understand where the proton and neutron mass come from. So, and they even understand what is the difference of the neutron and a proton mass. And I'm just presenting these rather old studies, beautiful studies by now, which I think have not been superseded yet. For lattice QCD, the most straightforward stage to address is the states that are strongly stable. And that is actually the botomonia represent the rich spectrum of strongly stable states. So this lattice calculation predicts many conventional botomonia, many multiplets. You see, they come in many spin parities, and then also predicts some unconventional states, which would be hybrid states, which have unconventional spin parities. Unfortunately, it's much more difficult to study the states that strongly decay. Well, that's because they are not asymptotic states of QCD. So if you want to study the resonance, and most of hadrons are resonances, then one has to actually extract the scattering matrix as a function of energy for this scattering if a resonance decays into this final state. And that's the aim of a theory. So if you extract the scattering matrix, then you can extract the mass and the width of a state from the cross section, or what I will mostly present in this talk, what you do is to look in the complex energy plane, where is the poles of the scattering matrix as a function of energy. So for a bound state, the pole would be below threshold, and this would give you the mass of a state. For a resonance, it will be away from the real axis, and the real part would give you the mass of the state, and the imaginary part would give you the width of a state. And one message I want to convey is that lattice QCD is by now quite good at determining the scattering matrices as a function of energy. If you want to determine the scattering matrix, for example, for this scattering, then you have to enclose two hadrons in a box and determine the eigenenergies of this system. And these eigenenergies will depend on the interactions of these two hadrons. And actually, Lucier has shown that from these eigenenergies, you can extract the scattering matrix as a function of energy rigorously. And that's how many resonances are now extracted from lattice QCD, and I'll show examples. In the Bethe-Salpeter approach, you search for poles in the scattering matrix by solving this equation, where gamma is a Bethe-Salpeter amplitude of a state. And actually, this equation is solved at the resonance energy. And just first results from this approach were obtained very recently. So here I'm showing you, for example, the results of both approaches for a sigma resonance, which appears in pi-pi scattering and has the vacuum quantum numbers. So for an example, on the left, you'd see study by lattice QCD, which simulated the pi-pi scattering and found that the pole of the scattering amplitude is actually located here, which quite nicely agrees with the PGG value. In the Bethe-Salpeter approach, the pole is found here. It's not exactly agreeing with the experiment yet, but I mean, this is not even expected because still some truncations are done and some simplifications, but I think this is a really nice progress on that front. Well, what really makes a life of a theorist complicated is that most of the resonances decay not only via one decay channel only, but via 2 or more decay channels. Then one has to actually study those scatterings, coupled channel scatterings, and extract the scattering matrix, which now describes all these coupled channels. And this is being done from the eigenenergies. So this you can determine from the eigenenergies on the lattice. And I'll show 3 examples, but it really is quite challenging tasks when there is more than one channel. When there is more than 2 or 3 channels, actually, sorry. So for example, this is the study of a conventional B1 resonance composed of light quarks, which decays into pi omega and pi phi. And HADSPEC collaboration has studied this coupled channel scattering. And here you can see the scattering amplitude for various channels as a function of energy. And you can see it is dominated by pi omega to pi omega in S wave, and it peaks around 1.4 GeV, which indicates that there should be a resonance here. So indeed, they find at 1.4 GeV a pole in the complex energy plane, which is not exactly in agreement with experiment, but that's not surprising given that the pion mass is bigger than in nature. Coming to more unconventional resonances, this would be a hybrid resonance composed also of explicit gluon, which couples to several channels, and the pole was found at really unphysically heavy quark masses. But the main conclusion is that this hybrid resonance resembles the hybrid pi 1 1564 state, which according to this reanalysis replaces 2 older experimental candidates for hybrids. Okay. Most of the exotic states found in experiment contain a charm quark and anti-charm quark. And so this is the only coupled channel study in this charmonium-like system. So the charmonium states and charmonium-like states can decay into DD bar. They can decay to D-sub-S bar. So this coupled channel scattering was studied. And well, the poles were extracted in the complex energy plane. Instead of presenting you the poles, let me present you the extracted masses of these states from the lattice and experiment. The main conclusion is that basically all the expected conventional charmonia are found with kind of the similar properties as in experiment, but 2 additional exotic scalar states are found also. The lower one is residing on DD bar threshold. So it's kind of probably a molecular DD bar state. It was predicted in many models, in several models by Osset and friends. And now it's also seen in the dispersive analysis of experimental data. The higher state is D-sub-S bar state. It is likely related to to this unusual state, it's called X3915, and it actually explains, this structure actually explains why this state has a small width to the Barrin experiment. Okay, let me give you an update on interesting developments in heavy light meson sector. Well, according to conventional quark model, you expect a triplet of flavor triplet of states. But new paradigm is getting more and more support from lattice, from effective models, and from reanalysis of the experimental data. And according to the new paradigm, actually, this fog component should be very important in addition to the quark anti-diquark. So according to this fog component, you expect a flavor triplet and flavor sextet. So basically, this is a triplet, that's a sextet, and all these states that are circled in blue, basically you should expect to feature in the spectra. And all the indications for all these approaches really indicate that these really feature in the spectra. For example, this exotic flavor state was found as a virtual bound state by the Hadron spectrum collaboration. And it should be a lower lying partner of the state X2900 found by LHCb. Coming to doubly heavy tetraquarks. Well, doubly bottom tetraquarks are not found in experiment yet, and they will be difficult to discover, but theoretically, these two doubly bottom tetraquarks are the only one that are expected to be really strongly stable and well below threshold. Actually, now all the lattice data and models agree on that they should be strongly stable. And here I'm presenting the binding energies from the most updated lattice calculations and some model calculations. And now we actually understand why they should be so strongly bound. And in the next slide, I'll give you actually how the masses of these states change when the B quark or U quark mass is changed. Okay, so the lattice data indicates then when the B quark mass increases, then the binding increases, which suggests that these two B quarks are bound by the color Coulomb force to a diquark with spin 1. Also, the binding increases when the light quark mass decreases, which indicates that the two light quarks form a good diquark. So this really supports this diquark anti-diquark picture. As for the other doubly heavy tetraquarks, with other flavors and other spin parities, actually theoretically no other state is expected to be significantly below threshold. These two are expected to be near threshold. But actually, theoretically, it's much more difficult to identify and establish a state near threshold or above threshold because you have to establish a pole in the scattering amplitude. And that is difficult for many approaches, for quark models and for many other approaches. And that's why the final conclusions have not been reached yet. And this is also reflected by the broad variety of the predictions for the doubly charmed tetraquark, which was predicted either below or above threshold. But now LHCb told us that actually doubly charmed tetraquark resides only 0.4 MeV below threshold, and taking the LHCb result and taking the kind of interpretations by the models, it seems that the likely fog component of this doubly charmed tetraquark is this molecular fog component of DD star state. And there is a subdominant component of diquark, anti-diquark. The only lattice simulation that actually extracted pole for doubly charmed tetraquark is the one presented here. Here, Padmanabh, Sara, and me simulated the DD bar star, so the scattering of D and D star, and extracted the scattering matrix as a function of energy. And we found that actually there is a pole in the scattering matrix, only 10 MeV below threshold. Well, this is done at unphysically heavy pion masses again. And what we find is a virtual bound state threshold. I think this result is kind of expected, and let's see why. When you increase the pion mass, the attraction in this channel is expected to decrease. So what you expect is to get from a bound state, which is seen by LHCb, you'll see a virtual bound state. So, but let's see what happens at more physical quark masses. Coming to exotic hadrons with heavy quark and heavy anti-quark, most of the states discovered in experiment are of this type. Well, and here I give few examples. Unfortunately, those are quite challenging for ab initio studies. And the reason is that they decay to a pair of heavy light hadrons, as well as to heavy quarkonium and a light hadron. So sometimes they have many decay channels. So only partial conclusions are available from ab initio studies. That's why I'll mostly review other approaches here. But if you're interested about ab initio results, this is a review here. Okay, so in this phenomenological approaches, usually the question is whether a state is a hadronic molecule, which would be basically composed of two colorless hadrons separated by some distance, and the attraction comes from the light hadron, a light meson exchange, or it's a diquark, anti-diquark, where which they interact by some gluons. Okay, first to the molecular picture, where I showed two vanilla candidates for the molecular states here. Well, this picture really shares many properties with the observed spectra. First of all, it predicts that states are near thresholds, which is in line with experiments. It predicts that the largest width is to two hadrons which are heavy light, and the rate to heavy quarkonia plus light hadron is smaller, which is in line with observation. And it also predicts, it prevents too quick decay to heavy quarkonium, just because the two heavy quarks are separated by some distance. Okay, so the mesons that are exchanged that bind those molecules are like pseudoscalars and vectors, and often the exchange of light pseudoscalars is prohibited by the parity conservation, and in this case the exchange of vectors is crucial, and that, for example, holds for this pentaquark here. Actually, a systematic study of molecules based on a single model predicts actually hundreds of these molecules from these flavors. Okay, it's based on vector meson exchange. It takes into account no coupled channel effects and mixing with the conventional charmonia. And if this model is correct, then there will be many more states discovered, and maybe then they will not be treated as exotic anymore. Coming to hadrons from diquarks, well, the fully charming tetraquark discovered by LHCb is an ideal candidate. For example, in this model, so this will be composed then of a diquark and anti-diquark, exchanging the gluons, and in this model by Giron and Lebet, the two interact via the potential computed on the lattice, and the diquark mass is fixed from the LHCb mass. The main conclusion from this approach is that actually you expect many states below the observed states by LHCb. So either these states are discovered, either they are too broad to discover, or they or the model is not correct. Then coming to this kind of tetraquarks, which contain also light quarks, as Umberto told you, there is many interesting features that and they observe several features in line with the data, but there is some drawbacks. Well, the gluon exchange is independent of isospin, so this model really predicts that states with isospin 0 and 1 should have the same mass. There is no way around this, and this is not yet reflected in the experimental data. Then since the two heavy quarks are really close in compact tetraquark model, then you expect a sizable width to quarkonium, heavy quarkonium, and some of the experimental states are narrow, and the ground state, according to this model, is expected to be scalar, composed of two scalar diquarks, and most of the exotic in experiment has spin 1. Partial solutions to all these were proposed. Now, if you're up to solving puzzles, here is one for you. These two by now famous states, doubly charmed tetraquark, this X3872, both reside within 1 MeV of the threshold in experiment. Well, and to me, it's puzzling why. There is some similarities, like they share the same quantum numbers. And in the molecular picture, they would be both attracted via light vector meson exchange. But there is some substantial differences. In the molecular picture, for example, this channel gets attraction from the pion exchange, while this channel gets a slight repulsion from the 1 pion exchange. Also, this channel here gets a contribution of important charm, anti-charm conventional Fock component, likely. And this channel would get an important contribution from diquark and anti-diquark. So, well, to me, it's still puzzling why they're degenerate within 1 MeV, but it will be fun to solve these puzzles. Well, before concluding, let me just show you states composed only of gluons, which come from QCD without C-quark effects. So far, there were only lattice results on this, but during the last year, we obtained also the results from beta-salpeter approach. So you'll have many glue balls with variety of quantum numbers. Okay, coming to conclusions. So first of all, compliments to experiments for really great results, which really make us go forward. It's really fun to work in this area. What's the status of Hadron spectrum from lattice QCD? Well, that really depends on where the state is located. So for states that are strongly well below threshold, these are straightforward and done. States that can decay strongly only via 1 channel have been done also. States that decay to more than 3 channels, that they are difficult. And honestly, many of the experimental interesting states decay via many channels. So that's why only partial conclusions are available. But I'm optimistic because there is a lot of improvement. But what is really difficult is that some of the resonances can decay into 3 hadrons, and that's very difficult, although significant progress has been done on this front. But from this, I think you can understand why the simulations are done at unphysically heavy light quarks still. This leads to a smaller number of decay channels, and honestly, it also leads to smaller statistical errors on energies and scattering amplitudes. As for the beta-salpeter approach, we've seen that strongly stable states are mostly done. And in the past year, we've also seen some nice results for states which can decay into 1 channel. Well, overall, for exotic hadrons, I think the main conclusion is that one picture cannot explain all exotic hadron states, but for each exotic hadron state, I think there is at least one viable picture. And well, and above all, theory predicts many more exotic and conventional hadrons yet to be discovered. So I think it will be an interesting future on both sides. So thanks for your attention. Well, thanks to my friends and colleagues for interaction.
Thank you very much, Sasa, for the really, really nice overview. Do we have questions? If not, I have one. You mentioned on the TCC slide that if we can go back, we have these.
Okay. Yeah.
Yeah. The
TCC. Yeah.
Actually, the one that comes later. Sorry.
Okay. Yeah. Okay, I see. Yeah.
So what do you see? Is there anything that can be done experimentally to better understand why this threshold is so close between those two states?
Experiment did a great job already, I think. But X has been studied by many collaborations. So for me, I don't know yet. Well, definitely on the TCC side, I would think that it would be great to see whether there is nearby state with other quantum numbers. And let's see.
Like, is there anything that one could learn if we can in the future measure TPB and the corresponding X state, and we observe a similar pattern? Is there something one could deduce from this for the double charm?
Well, TPB would of course be very great to discover. I mean, I think I would be really surprised that if this doesn't agree with the predictions. And I think the TPB is the real best candidate for diquark anti-diquark picture, right? The only really strong candidate. But TCC still, since it's so close to the threshold, I think it's not diquark anti-diquark only, but it will be also a molecular partly. So these two don't have exactly the same structure, probably, just because TCC is probably by coincidence so close to threshold. Well, well, what is good in the theory is that we can actually vary the quark masses, and then there we can kind of see how the poles of the states really depend on the quark masses, and then we can see whether the state is always near threshold when you vary the mass of the quarks, or not. So this can tell you something about the nature. Well, I think there is a lot to do in the TCC channel. For X, you did excellent job on experimental side.
Okay, thank you very much. I don't think we have any more questions. Otherwise, people can also follow up on Mattermost and in the chat with you. Then, yeah, thanks for the very nice overview. Then we have one last talk in the session from Giuseppe Bruno from Bari. That will give us an overview about heavy ion physics.
Hello, good morning. Just give
Hello.
To share my slide. Do you have it now?
Yeah, we don't see them full screen yet. So
yeah,
you
just I do it.
Perfect. Thank you.
Okay, thank you. So thank you very much. It's a pleasure to be here to give this experimental overview on heavy ion physics, and of course, I thank the organizer for asking me to do that. So I will introduce the field of heavy ion collisions, then discuss a few observable initial stages of probes where the bulk of the produced particles are, then our probes and few words about the future. So why to study heavy ion collisions? By colliding nucleus-nucleus to the elastic energy, we can create a droplet of the quark-gluon plasma, the system which filled our early universe. And the properties of this system and this evolution to the hadronic phase indeed had severe influence on the entire history of our universe. More in general, this is, I think, a common features of hadron physics. This is a very nice laboratory to study emergencies of complex quantum matter. We know very well the Lagrangian, we know how to do perturbative QCD, but still in other range, in other contexts, we still know very few. So I want to concentrate a moment on the phase diagram of QCD. Here we have this phase diagram, temperature, chemical potential, B, and one can have a system with mu b equals 0, which means a system with equal number of baryons and antibaryons, quarks and antiquarks, which is the system of our early universe, or the system reached at the LC or top rich energies. Or one can also have a system with QGP, say, doped with an excess of baryon quarks or antiquarks, which correspond to mu b equals 0. Experimentally, this can be studied by lowering the center of mass energy of the collisions. And indeed, there are rich experimental programs, both at RIC, the Beam Energy Scan, SPS, TFER, JESAI, NICA in Russia, and also in Japan. So any AV-ion program also has some reference colliding system like PP, DGO, which are fundamental part of this kind of studies. Today I will have no time to discuss that, but just I want to mention at LHC, those are not just reference colliding system. Very extreme proton-proton and PLED, where extreme emits events with extremely high multiplicity, have revealed really unexpected features which remember the quite close dose of AV-ion conditions, particularly the dynamical properties of this system. So still last slide of introduction, space-time evolution of a nucleus-nucleus conditions. Here we have this z-axis, direction of the beam, and time. Time 0 is the colliding time. Here we have the two colliding nuclei, and then in a very short time, less than 1 Fermi over C, much less at LHC, half a Fermi over C, a local thermal equilibrium is reached, the quark-gluon plasma is formed, but then the system expands, it cools down, at some moment the temperature will be that of the critical temperature predicted by lattice QCD, and the system will hadronize. There could exist a mixed phase. Still one can define two moments. The moment at which the particle abundances of the particles, of the different particles are fixed. This can be called chemical freeze-out. And those numbers correspond to LHC values, a temperature of about 150 MeV. The system can still interact, and the kinematic distribution of the particle can be changed during the expansion until really the system becomes so diluted that the particle can just freeze out and be detected. And this freeze out, thermal freeze out, is a temperature of the value of about 110, 120 MeV. So observable, knowing the initial condition, the initial stage is quite important. One thing is the centrality. With nuclei, one can have peripheral collision or central collisions, and those can be controlled at least quite well with simple geometrical model, Glauber model, which are known in the nuclear community since decades. By measuring simply quantity like the charged particle multiplicity in the events or the energy deposited at 0 degree with calorimeters. The variable used to quantify the centrality of the collision, a number of binary nuclear-nuclear collision, and called sometimes referred to as MB, or the number of nucleus which had at least one inelastic collision with another nucleus of the other nucleus. Number of participants. Then one can define classes of centrality which are expressed in the terms of percentile of hadronic cross-section. So we will find 0.5%, which means most central, 89% peripheral collisions. Also, one should keep in mind that the parton distribution function of the nucleons are modified, are affected by the presence of the other nucleons in the nucleus. So one can typically introduce nuclear PDF or nuclear modification to the PDF. Those are studied, determined and studied proton-nucleus collisions, ultra-peripheral nucleus-nucleus, or even nucleus-nucleus collision, but with probes blind to the strong interaction like with boson. Here, for instance, we have a recent CMS measurements of the Z0 boson as a function of rapidity as compared to expectation from proton-proton with those two sets of nuclear PDF, STEC15 and the DPS16. This current measurement, this measurement is actually underestimated by the nuclear PDF. Now I come to the second set of observable soft probes. There are several possible observable total multiplicity, which provide an estimate of the initial energy density, kinematic distributions, which provide information of the collective expansion, collective dynamics of the medium, the abundances of the different species, which gives you this chemical temperature and mu B, which is almost zero at ADC, but not zero at lower energy, two or more particle momentum correlations, or event-by-event fluctuation, which are quite relevant in this search of the critical point in the scanning of the phase diagram. So total multiplicity is a measurement at the square root of S energy for different collision systems, lead-lead, P-lead, here in this plot also proton-proton, and for different collision centrality, more central and peripheral. This relation derived by Bjorken in the 83 provide you an estimate of the initial energy density of the system, provided you know this equilibration time tau. So measuring this quantity, one can derive a lower bound. This lower bound is due essentially to the passage from the pseudo-rapidity to the rapidity and some assumption on the transverse sides of the system. So this is a lower bound of the product energy density time tau, and if one assumes a tau of half a Fermi over C, you will soon realize that the energy density at top for most central collision at the BC is up to a factor 20 GeV per Fermi cube or even 40, which is 30 times the energy density inside the proton, well above order of magnitude above the depth for the transition to be in place. As a second observable kinematic distribution of identical particles. Of course, one can measure PT differential distribution or more differential things like this azimuthal anisotropy. In this sketch, this reaction plane is defined. Z is the direction of the two beams. For non-central collision, you will end up with a fireball interacting nucleons, which show an anisotropy in the geometry, in the geometrical space. Due to the different pressure gradients in the in-plane direction, this direction, with respect to the out-of-plane direction, this initial geometry anisotropy is converted by a collective dynamics of the system in an anisotropy in the emission of the emitted particle. This is in the transverse plane with respect to Z, and this is the angle measured with respect to the reaction plane. So one can measure this distribution and express this as a term with a Fourier expansions. The first non-null coefficients, V2, which is the most relevant one, quantify the so-called elliptic flow. So here we have these V2 coefficients as a function of PT measured at Rick, Phoenix, and star for pions, kaons, proton, lambda, and cascades as a function of PT. And you observe an ordering with the mass. Then by simply plotting the same quantity as a function of the transverse mass, the rest mass, you obtain a grouping for mesons and baryons. And if you scale by the number of constituent quark, 3 for baryons and 2 for mesons, of 2 and this transverse mass, you obtain a very nice scaling, which is suggestive of the fact that most of this collected dynamics develops when the system is in its partonic phase. As I was mentioning, the model, relativistic and dynamical models can describe quite well these distributions, and they also have introduced some friction and with a ratio of the shear viscosity over the entropy density close to the quantum limit, which brings to the conclusion that this is really a perfect, almost perfect fluid, the quark-gluon plasma created in this kind of conditions. As I was mentioning before, by measuring the abundances of the different particles, one can retrieve information of this chemical temperature and also on the biochemical potential, which PVC is close to 0. So here you observe how simple statistical thermal model, where the only parameter actually is temperature and the biochemical potential plus the volume, just to give you the absolute production, can describe the measured yield from pions up to omega, the deuteron nucleus, even hypernucleus, over 7 orders of magnitude with quite a very good precision. Those lines here. It's fair to say that it works equally well at SPS and weak energies. Two-particle correlation. So historically, typically this is done with identical particle correlation, the so-called Embury-Brown and Twist interferometry, which provide information of the system size. This is not really day one measurements, say month one measurements. Now that after knowing very well the system size, even better in proton-proton collision, which is almost point-like, one can use a similar technique instead to study different things, the strong interaction. So to study strong interaction among rare hadrons. This is sketched here, the concept. You need to have two hadrons which are very close in momentum, K star being the momentum difference, essentially. And depending on the potential interaction, for instance, it could be repulsive or attractive, we will end up with a very different correlation as a function of the momentum difference. Alice, for instance, measured a proton psi, proton omega, even proton phi correlation, and from that one can retrieve information, quite relevant information for hadron physics, on the interaction, on the strong interaction. I'm afraid I'm a bit late. I will just go very fast on that. Event by event fluctuation are very relevant in the search for this critical point. I forgot to mention before that lattice QCD predicts a first order phase transition in this region, while at mu b equal to 0, the phase transition from the quark-gluon plasma to the hadronic phase should be a crossover, which means that there should be a critical point. And cumulant of conserved quantity like baryon number, charge, or strangeness, I expect to be very sensitive. In particular, non-monotopic variation of higher order cumulants should be observed close to the critical point. There has been a recent claim of an observation, this is still an observation by Starr, of a non-monotonic dependence as a function of square root S of the net proton, which is a good proxy of the baryon number conservations, which you can see for most central gold-gold collisions around here, while peripheral collision of model indeed predict Poissonian-like fluctuations. But still, I would say that the critical point is still eluding experimental evidence. A similar measurement has been done by NA61 at SPS, and both Starr and NA61 have in the future further campaign where we will accumulate larger statistics for this kind of studies. I come to last group of results, are probes in nucleus. They are relevant probes for essentially for the following motivation. They are produced in partonic collision, in the very early stage of the collision, in partonic process with large Q square. The formation time of this IPT particle or heavy mesons are very short from the simple energy time uncertainties. And simply because of the higher PT or the higher mass, the formation time is very short. So they really explore the full evolution and study the modification in their production between the nucleus-nucleus and proton-proton. One can infer information about the properties of the medium. A variable which is used is nuclear modification factor, which is the ratio of the nucleus-nucleus versus PP, normalized to the different number of collisions. I start with jets. Those are the very first ever display with the calorimeters, in particular of ATLAS and CMS, where one could observe sort of monojet events. One jet emerged from the quark-gluon plasma. The other jet was essentially quenched. So for the jet, what we expected somehow I learned, jet are indeed quenched in nucleus-nucleus. This is this nuclear modification factor versus PT for more central and more peripheral, a result by ATLAS, up now to an energy of 1 TeV. The jet in the medium appears softer. This is the ratio of the DZ distribution between lead-lead and proton-proton. So one observes an enhancement of particle carrying a small fraction of the jet in lead-lead with respect with PP. And this increase with centrality not shown here, and also with the jet transverse momentum, as you can observe here. The hard core of the jet get narrower in the medium. To study that, one can define the girth, the width of the jets. And this is a measurement by Alice in lead-lead, this black point, as compared to Monte Carlo, which are essentially tuned on proton-proton results. So you can do the ratio of lead-lead over Monte Carlo, proton-proton, you can consider, and you observe this hardening of the core. Finally, the soft power, the energy flows, the soft power diffuses to large angles. This is again a ratio between lead-lead and proton-proton. In this case, the ratio between the distribution of the charged track in annular ring around the jet axis. So this is the function, it's a function of delta R of the jet. An interesting result is that to study more differentially, not just inclusive jets, which are produced as by an original parton, which can be either a quark or a gluon, mostly a gluon, in particular in this PT range. One instead, by tagging a jet with either a photon in the other direction or an electroweak boson, we can have, first, we are confident that this jet would have originated by a quark, and so we can study the different energy loss of quark with respect to gluons. But more importantly, we have information about the original momentum and direction of the jet, because in studying inclusive jet, you can study only what is the reconstructed momentum and direction. Instead, you would be interested in the original. So at least at the leading order, both Z and gamma target jet, isolated gamma, provide PT and azimuthal direction of the partner of the reconstructed jet. The difference is that, of course, isolated gamma target jets were soon studied at the LHC. Now we are also studying Z target jet. This is a measurement by ATLAS. Again, with a ratio, this IAA is the ratio of the per Z yield in lead divided that in proton-proton. One can observe a softer PT distribution with a suppression at higher PT. If one, and this is as a function of the PT of the charged jet for different range of the PT of the Z boson, higher PT, intermediate PT. If one concentrate on the most central condition here and compare with the model can catch this rise, this softening, all included very dedicated description of the back reaction induced by the medium recoil, and even jet-induced medium excitation. If you are interested, you'll find details in the car. So open and be flavored. No, just because of their large mass, those are also hard probes. And once produced, the production of CC bar is happens by perturbative process, and there is no sizable thermal production. The hadrochemistry, the production of the relative species, depends only on the way the hadrons are formed. Why in proton-proton, typically you have hadronization by string fragmentation. By fragmentation from a quark-gluon plasma, you can have a production by the coalescence of the the coalescence of two quarks from the medium. That's the reason why, for instance, the Disa base is more productive as one would expect with respect to proton-proton. This is the ratio to the zero of the D mesons and on the lambda, and also on the charmed baryons. So these thermal models works also well in describing this. What was really surprising at ABC was the fact that already in proton-proton collisions, the charmed baryons and also the beauty also basically reported something similar in the beauty sector, were much more abundantly produced than expected from the fragmentation function, which are obviously tuned mostly on the plasma and results. Now I go back, instead of speaking more, as I was doing this slide on the hadronization mechanism quite fastly, but still I wanted to discuss that. I will go back on the role of this particle in the study of the properties of the medium. They are produced at the early stage, they traverse, and differently from jets, IPT particles, which are mostly coming from an initial parton, which is a gluon. Knowing that this is a D meson, and D meson essentially tell you that the original parton was a quark. So the energy loss of the parton in quark-gluon plasma should depend on the color charge. The gluon has a larger charge, a larger Casimir factor than the quarks. On the parton mass, the charm is still essentially a light object with respect to the beauty. So at the parton level, one would expect this disordering in the energy loss in the quark-gluon plasma. So a naive expectation should be the nuclear modification factor of the pions, which are mostly for the gluon, larger than D meson and larger than U. Indeed, this was more complicated due to the different production kinematic and fragmentation of light and the quark, and this was soon understood with the first LAC round 1 data. As you can see here, this is a model where you introduce these details and you perfectly describe D meson in black and light pions in green. While that was one of the main results from round 1 LC data, the fact that the energy loss of D meson was smaller than that of D meson. Those are known from JEPSI by CMS and D meson by others. With round 2 data, we could collect a really wealth of data in this sector. This is a very nice compilation by CMS, now measuring even the Bissell C nucleus, which is very difficult. And one observed a similar suppression for Bissell S and Bissell C. At IPT, there is indication of a common behavior. And this, please keep in mind, it has a log scale up to very high PT. While studying this, considering this kind of array, one should also always keep in mind that the PT range still drives the physics behind this mechanism. So at high PT, radiative energy loss process, gluon emission, radiative gluon emissions dominate the energy loss. Instead, in these intermediate PT regions, collisional energy loss mechanisms are relevant. And instead, in the very low PT, where, however, the bulk of the production is concentrated, as you can see, if you see the PT distribution instead of the ratio between lead and proton-proton, this recombination mechanism of quarks from the quark-gluon plasma becomes very important, even dominant for the GIPSI. So also going to lower PT is quite important. State of the art after run 2 for area in the flavor sector and also these two quantities which I've introduced earlier are likely those plots compared to 3 models. These 3 models have different implementation of the radiative energy loss, the dependence on color charge and the parton mass and path length of the partons in the medium. While instead going to lower PT, you can again have now very precise measurements, which really put stringent constraint on the state-of-the-art of models, and the ingredients of the models in this PT range to describe at the same time these 2 variables are the transport of C-quark, which is done with either a Boltzmann or Langevin approach, C-quark energy loss again, and also at low PT, the hadronization of C-quark with this coalescence mechanism. Last couple of slides, last subject, quarkonium. This was an historical signature of the quark-gluon plasma. The system is so hot that the state with the lower binding energy will dissolve. And I will start by showing the first somehow predicted but surprising result at LHC. This is GIPSI array, nuclear modification factor, as a function of centrality, measured at LHC and at RIC, at lower energy. It was quite surprising at the beginning, even if predicted, to find an almost a larger suppression at lower energy where the temperature is larger. And this was understood and explained as due to this recombination mechanism. At LHC, the number of CC bar pair is so rich and the density is so high that there is very good probability of a recombination of CC bar pair to reform a GIPSI. And indeed, at mid-rapidity, there is a larger density, and one observed smaller suppressions. And as you can see here, for A as a function of PT, this is where the bulk of the production of GIPSI is concentrated. This is indeed a low PT, and this rise in the model are justified only by this recombination mechanism. Upsilon, this is a CMS spectacular results with invariant mass of the upsilon in lead as compared to proton-proton, which has essentially no statistical uncertainties. You could see by eye how the upsilon tri-S is completely melted, dissolved. The same similarly also for the upsilon 2S. And this suppression of the upsilon 1S can be simply explained as the suppression deriving from the feed down of the upsilon 3S and 2S. Also, upsilon put very significant constraint on different model, different approach. There are details in the backup if you are interested. Those are array measuring for upsilon 1S and 2S by ALICE and by CMS as a function of the centrality of the collisions. I come to my last slide, outlook. I could not really discuss into detail, but there is a broad program to scan the QCD phase diagram. The second beam energy scan at RIC. At SPS, there is running and with a program approved for next year's NE61 and SHINE, proposal of a new experiment, NE60 plus, to study d leptons, and they open indeed the NEVI flavor. FAIR, JSI, NICA, and also JPAC in Japan. At very high energy, LEC and RIC. SPHENIX is a new experiment under construction, which we should work before prior of electron and collider. We will exploit at LEC run 3 and run 4, in particular now with the major upgrade which took place during the long shutdown 2 of the ALICE experiment. There is a proposal to be run during the luminosity phase of LEC for a new experiment to replace completely ALICE in point 2 of LEC, so start late there in the 30s. And also it's worth to mention that AVIO physics is always mentioned as a part of future circular collider itself. Thank you so much for your attention.
Thank you, Giuseppe, for the really nice overview. Are there questions? If not, I have one regarding the Upsilon signature that, or the suppression that you saw at CMS. Can you comment a bit more about the different models that are shown here?
Yes, sure. This is this first one is a model where one defines. This is an historical model introduced since the time of the SPS in the 90s of the past centuries, where one defines co-movers, which could be whatever objects, or you have just as a single ingredient a cross section between this object, which could be even some hadrons or whatever's. And of course, you have to introduce as well nuclear modification to the PDF. So in this model, it's not really the temperature, so it's somehow a phenomenological model that can describe this suppression. While instead, this one is really a transport description where you describe with this Langevin or Boltzmann approach the transport of the V bar in the quark-gluon plasma with an evolution with a balance equation, I think, between dissociation and regeneration. And of course, you also need to have nuclear modification. And this is a bit more similar to this transport description, but done actually in a hydrodynamical approach. Even further, if you like, detailing the backup, but maybe you want to check if there are other questions before. I don't know. Please tell me.
Thanks.
I hope to have answered.
Okay, then are there more questions? Like everything was crystal clear. Then thanks very much, Giuseppe. Then this concludes the current plenary session. There's a break. I don't know if the organizers want to say something more.
Not more to add. Thanks very much to you for chairing and to all the speakers, and we'll